Okay, so today we're going to be talking about Newton's laws of motion, and this is going to be a good overview of forces, and it's going to serve as a good conceptual review as to why objects move the way they do, so whether they accelerate or stay at a constant velocity. Okay, so this year we have been working really hard to develop a model of how things move. Now, we started the year first talking about acceleration and velocity and how they're both related to each other, and how acceleration is just a change in velocity and velocity is just a change in position. And we spent the first couple of units doing that. And then we start talking about forces, and the reason why we started talking about forces is because we wanted to gain an understanding of why objects move in the way they do. After Unit 3, we already became experts in how objects move, but now we wanted to know why, and it turns out that it's all about forces. And I first began Unit 4 by saying that a force is an interaction between two objects that results in a push or a pull. And then we did a hovercraft lab where we analyzed video of me riding a hovercraft, and we were able to conclude that if the forces acting on the system are balanced, then the system moves at a constant velocity, and vice versa. So if a system moves with a constant velocity, then the forces acting on it are balanced. Those two ideas are always together. And likewise, we know that if the forces acting on a system are unbalanced, then the system is accelerating, and vice versa. If the system's accelerating, we know the forces acting on the system are unbalanced. Now, towards the end of Unit 4, I brought out the push plates and the force sensors, and we did a tug of war or push of war, and we noticed that if object A exerts a force on object B also exerts a force that's equal in magnitude back on object A, but in the opposite direction. And most recently, we have been talking about the net force in Unit 5. So this fourth statement was from Unit 5, and it's been the equation that we've been mostly focused on. And it turns out that this equation here really also works for the balanced system too. Okay, you'll notice that if the forces were balanced, acceleration 0, which means there is no net force. So the forces are balanced. Okay, so if we have a 0 on the right side, we also have a 0 on the left side. So that still works. Now, acceleration is not 0, and we learned that the net force is equal to the system's mass times its acceleration. And we learned this with the modified Atwood oscillator lab. Now, my own personal feeling about teaching physics, I don't really prescribe to defining Newton's laws of motion, but the final does make mention of these things. So it's important to walk into the final and understand what each one is with respect to what we've been doing. And it turns out that you should see striking similarities between Newton's laws of motion and what we've been talking about. So the first one is Newton's first law, which says an object moving at a certain velocity, which, reminder, this also includes 0, will remain at this velocity unless it experiences a net force, or unbalanced force, the same thing, right? A net force is an unbalanced force. The second law is a system accelerates when the forces acting on it are unbalanced. So there's a net force. Again, those two are the same thing. This net force is equal to the system's mass times its acceleration. So this should be super familiar. And Newton's third law says when a body exerts a force on a second body, so in this wording, by body we mean an object, the second body simultaneously exerts a force equal in magnitude and opposite in direction on the first body. So does this sound familiar? going back to the slide before that, it turns out that this is exactly what we've been talking about. Now, the first thing doesn't really isn't really one of Newton's third laws, but it is an important one. It's the definition of a force, while also giving an important nod to Newton's third law, where a force is an interaction between two objects A and B. So when I was introducing the concept of force and defining it for you, this is really a little foreshadowing, I guess, for you English students there, a little foreshadowing that something was going to happen because, you know, we want to be efficient, and I wanted to make sure that every word was important. So this interaction between two objects is extremely important when we're talking about forces, because people often forget that when an object exerts a force on the other object exerts a force back in the equal in magnitude, opposite direction. Now, the hovercraft lab, this was just Newton's first law. If forces are balanced, then it's going to remain doing what it's doing. And if the forces acting on a system are unbalanced, then it's going to change its motion, or it's going to change its velocity. So in other words, it's going to accelerate. And we just talked about Newton's third law, and finally, Newton's second law is almost word for word for what we did. So Unit 5 was really about Newton's second law, and we did do the forces out of order, but instructionally, I believe this was the best route to take. One other thing is that I also personally chose not to make mention of the word inertia. Inertia is a property of matter that indicates how resistant it is to changes in motion when it experiences an unbalanced or net force. Okay, it seems very wordy, but really, let's break this down. Think. What property of matter determines whether it can easily be accelerated or not? So think about that for a second. So it turns out inertia in this class is just mass. These two things are synonyms, and it's a very important thing to kind of know, as there is a question on the final that will make mention of inertia. So this is another vocabulary thing that we want to get straight here. Inertia is just mass, okay? And these are synonyms, and it kind of makes sense when you think about it. Let's say we have two objects, a massive object, a small object. Let's say the goal was to accelerate, to make sure that these masses reach an acceleration of 10 meters per second squared. Think, is it going to be easier to accelerate, to give the larger mass a 10 meter per second squared acceleration, or is it going to be easier to give the smaller mass a 10 meter per second squared acceleration? So clearly, a more massive object is going to be harder to accelerate. So it's going to require a larger force. Okay, and that hopefully should make sense. So likewise, if you're going to double an object's mass, you're essentially doubling its inertia. Likewise, if you're going to triple an object's mass, you're tripling its inertia, and that's all that really means. More massive objects require a greater force and cannot be accelerated as easily as a less massive object. And that's pretty much it. It's a quick conceptual overview of forces and Newton's laws of motion.